going to press record now, and here we go.
All right, well, thanks everyone for joining us on a Friday evening. I think this is a great way to start the weekend, talking about some building science. And we have Graham Finch here today to remove the confusion of water vapor diffusion in the design of building enclosures. So this is hosted by the Engineers Yukon Continuing Professional Development Committee as a part of National Engineering Month activities. So if you've been to the website to register, there's a great slate of events all through the month there. All are available free of charge and are on a wide variety of topics, from traditional Indigenous technology to project management to net zero emissions. So make sure to go check those out if you're interested. I'll put the link in the chat so everyone has it there. And today we've got Graham Finch, a building science engineer with RDH Engineering, who specializes in enclosure design, research and investigation work for new and existing buildings. Much of his recent work has focused on highly insulated building enclosures, including some specific research and the publication of a few really interesting guidelines for new and existing buildings up here in the Yukon and Northwest Territories. And I'm sitting in Whitehorse here today. So for, I guess, housekeeping, we're going to have everyone on mute through the presentation here, but if anyone has any questions, please use the chat feature, and we'll kind of be monitoring those and maybe answer a couple as we go and pick up the rest of them at the end. So I guess with that, I will turn it over to you, Graham.
All right, thanks, Tyler. Let's share my screen here. All right. Perfect. All right, I really thank everyone for showing up on a Friday afternoon. We are talking about building science, and building science this time of day usually deserves a cold beverage. For those who have a cold beverage in front of them, we're going to do a little building science experiment, so we can all understand what we're talking about today. So if you've got a cold beverage, say a beer or whatever it is in front of you, depending on where you are, thank you, Robin, depending on where you are in Canada and how dry it is indoors, you may find that you have some condensation on your can, depending on how cold it is. Hopefully it's just cold to get some condensation. So today we're going to be talking all about condensation in buildings, and not necessarily a bad thing on a beer can, but it is a bad thing on in your building. And so we're going to be talking about vapor diffusion, condensation, and how this can be a challenge and something we need to address within wall assemblies and cold areas of our buildings. So next time if you're picking up a beer or cold pop there later on or whatever you're drinking, next time you see this, you're going to think of building science if you're not already. So I'll save this for later. Drink water during the presentation so you can all understand me. So today, this afternoon, we're going to talk about vapor diffusion as a building science construct and a phenomenon. And we're going to talk about how vapor diffusion is controlled and how what problems it can cause and how we address it in buildings. I'll talk about some tools, I'll talk about some case studies, and we'll generally by the end of this hour, hopefully have a good appreciation what vapor diffusion is and how we can address it in buildings. Aware that a lot of people on the call here aren't necessarily in the building science field or building enclosures field. We're coming together from all parts of the country and all different disciplines of engineering and other interests. Building science is, like it sounds, the science of buildings, and the science of building enclosures specifically. And it touches on all aspects. It's on how building materials in enclosures perform, energy efficiency, thermal efficiency, condensation, structural performance. The building enclosure is the aspect of our piece of our building that separates indoors and outdoors. And by separating that indoor and outdoor environment, which is conditioned on the inside, really cold or hot on the outside, it's uncontrolled on the outside, really cold in the wintertime. The building enclosure is separating those two dissimilar environments. And by separating that, we have a loads across the building enclosure. but a number of things we need to address. So we need to address water penetration in the form of rainwater, groundwater, even snow and snow melt, condensation, airflow. We don't want air flowing through the building in either direction for comfort and for condensation reasons. Vapour diffusion, which I'm talking about today, is a portion of what we're looking at. Heat flow, and then light and solar radiation, and of course noise, acoustic side of things, fire and smoke. So the building enclosure is doing a lot of things within a building. At the same time, it has to transfer structural loads, and there's requirements for it to obviously be durable and maintainable. The economics of building enclosures and what you use and how much insulation you put in, it's a big part of the decision process and the economics of making that affordable. And of course, constructible. We need to be able to build these in an efficient manner. And to the general public, the building enclosure is what you see on the inside and the outside. And there's a lot of stuff and a lot of layers in between. And we're going to dissect the layers today to understand all those pieces. So when we look at, just going to close this off here. Hide this. Thank you. Zoom is giving me a little. So when we look at buildings, how they get wet and how they dry out. So today we're going to be talking about controlling moisture at the microscopic level. That's what vapour diffusion is. We'll talk about the other mechanisms as well. We're going to specifically dive into the small pieces today. Building enclosures get wet by a number of mechanisms here. We got precipitation hitting a wall. We got water vapor that's transported by diffusion and air movement, both outward and inward, or inward and outward through the building. We've got built-in construction moisture, and then we've got groundwater. So these are the areas of wetting that we're primarily concerned about. On the flip side, we got our wetting side, we got our drying side. On the flip side, on the drying side of things, we have evaporation at surfaces, and there are surfaces of the cladding and also materials within. We also have water vapor transported by diffusion and air movement, both outward and inward. We have drainage by gravity, and then we have ventilation, drying by air exchange, which encourages evaporation off the surfaces. So vapor diffusion appears on both sides. Buildings can get wet by vapor diffusion, but they can also dry out. And what's becoming more important to look at carefully, especially with more highly insulated building enclosures, is the drying side of vapor diffusion. Vapor diffusion is often the only way that some wall assemblies or roof assemblies, for that matter, can dry out. So it's a very important part of durable design. In the context of things, vapor diffusion is small, and we do care about it, but it's one of the smaller loads and the smaller moisture sources we have to contend with. So an example, if you look at a 4x8 sheet of drywall, and if you looked at the amount of moisture that might be transported through that drywall over the course of a month, you might get 1/3 of a liter of water diffusing through. We'll talk about that mechanism more here today. You might get 1/3 of a liter of water, right? So about a cup of water. That same sheet of drywall, if you had a little 1-inch by 1-inch hole, air leakage over the same period of time would probably bring 30 liters of water across. And so if you had a hole in your wall, in your air barrier, so to speak, you would get 100 times more water than you'd have by vapor diffusion. And then if you're in areas that get a lot of rain, the rainwater could be like 300 liters of water through that same hole. And so it's important to realize that diffusion, and we're talking about very small amounts, but small enough amounts of moisture that can still cause problems. And of course, we need to address air leakage and rainwater leakage as well, but subject of another session. Water vapor versus liquid water. And this is important to distinguish as well. So today we're going to be talking about vapor. And vapor itself is, if you look at a water vapor molecule, or H2O, it acts as a single molecule. It's very small, right? Versus liquid, which is clusters of 60 or more molecules or so. It creates small droplets of liquid. And so when we talk about vapor transport, it's actually the individual molecules rather than liquid, which we can address in other means here. So it's very small, and because we're looking at a single molecule, it can actually go through a lot of things. So when you look at building materials, so we call them porous materials. Porous materials act as screens. Okay, so materials We imagine this hypothetical material here where we have holes where the water vapor molecules will fit through it, but the liquid molecules are too big to go through the screen, just like your window screen, right? Bugs can't go through, but little tiny no-see-ums, right, can, right? And so the material can be resistant to liquid water, but vapor permeable. And there's lots of great examples of this, Gore-Tex jackets, Tyvek, a lot of house wraps, where something repels water, but it's still breathable. The marketing term would be breathable. And what that means, that breathability, is that water vapor can go through, but liquid can't. Okay, so we have these materials that can act as screens. Water vapor diffusion is the movement of water vapor molecules from a concentration of more to less, or we like to think about high pressure to low pressure, and it's governed by something called Fick's law. Vapor diffusion is quite slow, and it's the process of water vapor molecules that occur through tiny pores of materials. Okay, diffusion can cause wetting of cold materials and condensation, but it also can allow for drying of concealed wetting materials. So if you have, wet materials or wet wood in your wall or wet insulation, the only way to dry that out is it diffuses through by that difference of vapor pressure, or you'd have to open it up and allow that moisture to evaporate out, which we can't do in concealed assemblies. So diffusion is how we dry things out, or we design assemblies so they can dry out. A lot of materials that we use in construction will slow down or stop the process. And that's what we call vapor retarders or vapor barriers, and it may be intentional or unintentional. So when we look at diffusion and airflow, there's often a lot of discussion in our industry about air and vapor barriers. And so there's a lot of people will look at a material and say, oh, that's an air vapor barrier. We're intentionally breaking that apart here in a lot of the discussion. And we need to look at vapor diffusion separately from air. They're two different transport mechanisms. They both move moisture. It's important to realize that diffusion and vapor diffusion, which we're talking about today, occurs from a high to a low state, right? So it's either dew point or water vapor density or vapor pressure. They're all the same things, just we call it different things. So a high vapor pressure to a low vapor pressure, lots to little, right? And so there's this flow of moisture. The molecules want to come to equilibrium from a high to low pressure. When we talk about airflow and air transport and air barriers, not today, it's talking about a high air pressure to a low air pressure. And there's a difference between air pressure and vapor pressure. Okay. So when you look at a material, so we have here in the example, we have a material and we have air on one side and air on the other side at a different vapor pressure. On the left-hand side, we've got a higher vapor pressure than the right-hand side. Now, water vapor molecules aren't smart. They're randomly bouncing around, and this is all about probabilities. And so interestingly, water vapor molecules are bouncing through in both directions at all the time. But what happens is the net effect is that where there's a high vapor pressure, low vapor pressure, you're getting more molecules coming from the high side to the low side. And therefore you're getting a net flow of water vapor by diffusion. So the process of diffusion is driven by vapor pressure differences, which you can visualize just by like a number of molecules in that space, right? So this side has 6 and this side has 3. So the vapor pressure is twice as high on the left-hand side to the right. And so the probability of the vapor flow going to the right is twice going to the left. And so that's what vapor diffusion, the net effect is the diffusion, even though things are going in both directions. And so we have something we call vapor drive. And so the net effect of that vapor pressure difference and the diffusion through the material is vapor drive, right? Many people on the call probably haven't seen something that engineers use called a psychrometric chart. So a psychrometric chart, some people call it psychopathic chart, and the voice captioning here did not at all capture that, but psychrometric. Psychometric chart is something that mechanical engineers and building science engineers will use to look at, to essentially, a nice chart that you can quickly look at and understand differences in vapor pressure. It's essentially a 3-axis chart where we've got temperature and vapor pressure, and then you got curving lines of, in this case, relative humidity. And so if we want to understand vapor pressure and where the high vapor pressure side, we can look at sort of states of conditions here. So indoors, most of the year, will vary typically 40 to 60% humidity, quite a bit lower in the north, as you know, in the wintertime. But let's just say 25 to 50% humidity indoors, 20 to 23 degrees Celsius. So the vapor pressure indoors is 1,000 pascals plus or minus, a couple hundred. Okay, that's where we generally live. When it's really dry and indoors and our skin's cracking and our beers aren't condensing on the outside of the cans, it's going to be probably on the low end here. When we look at outdoor conditions in the wintertime, anytime it's below freezing, you can see the vapor pressure is below about 500 pascals. And so generally what you find is the vapor pressure all across Canada is higher indoors than outdoors. And even if it's raining, 5 degrees and even 100% humidity, the vapor pressure here will often be lower than it is indoors. And what makes the indoor humidity or the indoor vapor pressure high? Well, we live indoors, we generate moisture, we shower, we have materials that are evaporating, we walk in with wet clothes, we breathe, we have pets, we have plants. And so all these things increase the moisture load, which tends to result in higher vapor pressure indoors than outdoors. And so generally, when we talk about vapor diffusion in building enclosures and buildings, it goes from inside to outside. So if we look at vapor diffusion through, say, an insulated wall, we got left-hand side, so we've got higher vapor pressure inside, we got outdoors on the right-hand side, we got a high temperature, and as we go through an insulated wall, what happens is the temperature drops, okay? And as the temperature drops, the amount of moisture the air can hold, it reduces, and we get to a point we call a dew point, and at this dew point, the air can no longer hold the moisture in there, and we get condensation on typically the next solid surface. So if we have a 2x6 wall with bad insulation and we didn't have a vapor barrier on the inside, what would happen is we get vapor molecules going through the drywall on the inside, and we would actually get an accumulation of moisture and condensation on our plywood or our sheathing on the outside. Now, this is not new. This has been known for some time. When insulation was, in the 30s, sort of first developed and commercially sold, it was sold typically without a vapor retarder on the inside. So they put insulation into the wall. And in many cases, there were a lot of building enclosure failures where siding, the paint would blister, and we get mold inside our walls here. And so very quickly, the insulation industry realized that if you add insulation and change the temperature profile across a wall, then you also need to address vapor, okay? And so visually what this looks like, so here's a wall, a fiberboard wall out of a testa here. You can see the insulation, and this is vapor diffusion, actually condensation, actually frost, because it's a case where there's a freezer on this side, like it would be up north. As you can see here in the picture, all this frost that is accumulated in the outer inch or so of insulation. So this is a visual representation of what vapor diffusion condensation, or in our case here, frost looks like. So when we look at vapor diffusion problems in building enclosure assemblies, things like walls and roofs, it typically shows up all across the surface, right? It's something that it's a one-dimensional phenomenon, but it occurs, persistently across the entire enclosure. And so when we see vapor diffusion problems, or in the case here, there's actually ice forming on the inside of this concrete wall. So in the case here, someone put some bad insulation on the inside of a concrete wall that was above grade and freezing, and no vapor control on the inside, and there was ice over the entire thing, and it would just ice up every winter, and then it would melt in the springtime and thaw out, and it would all run out to the inside of the building. And that's a classic sort of vapor diffusion problem. Now, we usually don't see vapor diffusion problems because, in 2021, the industry's generally got this figured out, although we still run into case studies and we still run into weird little things, and that's what I'll share today as well. So when we get into controlling vapor diffusion and preventing that condensation or frost from occurring, so we like insulation, keeps us warm, keeps it comfortable, and it's necessary for energy efficiency. The way we address this in a simple form here vapor diffusion is we put something called a vapor retarder, or some people will call it vapor barrier, and we'll get into the nuance what that is in a bit. But we'll put something to retard or slow down the flow of vapor on the high vapor pressure side. So essentially we put it on the inside, right? So we got high vapor pressure on the inside, low vapor pressure on the outside. But we put a vapor barrier on the inside of the insulation. And what that's doing is it's preventing the molecules from getting through into the insulated or cold space, right? So we have to put it on this side, because if we put it on this side, the molecules would just go through all the materials. So we put it on the side we want to stop the molecules from getting into. And it really is that. It's a molecular level sieve, so to speak. You're essentially throttling as much as you can, as much as you need to. So vapor retarders and vapor barriers, we use the term loosely in the industry, and we shouldn't, but it is sort of the way that people talk in our business. A vapor retarder, what we're talking about here is vapor retarders in general. So a vapor retarder is a material with properties that significantly slows down or retards or slows down the diffusion of water vapor through an enclosure assembly. And we have units, and I'll talk about how the units are determined, but we have something like 1 US perm to 10 US perms, or we might talk about 57 nanograms, right? That's a billionth of a gram per pascal, vapor pressure per second per meter squared. So very, very small amounts of mass by vapor pressure over time. And so sort of units like this, we generally, from simplicity, because they're simple numbers like 1 to 10. Products like wood, foam insulation, and vapor retarder paints, things like that, those are vapor retarder or materials that are sort of fall into that level of permeance. A vapor barrier is another term that we use a lot. And a vapor barrier is essentially something that, when we're talking about barrier, for all intents and purposes, it practically stops diffusion of water vapor through an assembly. So it does a bit more than retards, it actually stops. Or for practical purposes. And so vapor barriers, we tend to talk about them being impermeable and something less than 1 perm. Things like polyethylene sheet, metal, glass, asphalt roofing, peel and stick membranes are generally falling in this class. Okay, so vapor retarders are a bit more open to the molecules than a vapor barrier. Okay. Now, when we talk about vapor barriers, the majority, even the public, you go to a Home Depot or a hardware store, wherever you are, you're going to find this plastic sheet, and it says, can ccSPF, it'll say vapor barrier all over it. And you've seen this plastic probably in your basement, maybe in your ceiling, maybe in your walls, maybe during renovations. And that traditionally has been thought about as the vapor barrier that we put in. Now, what's changing in the industry is we're adding more and more insulation, different types of insulation, building the assemblies differently than we have in the past. And so this notion of this is the only thing that can be a vapor barrier is quickly disappearing. But it's still there. It still is a vapor barrier, of course. Now, when we talk about measuring that permeance, there's actually a test to do this. It's an ASTM test. And they have these cups. And essentially, the cup has desiccant, so 0% humidity, or it has water in it, or you flip it upside down. Almost did with like water there. So you have your cup, your water, you put your material on top, and you just measure the mass loss through that, and then you measure a vapor permeance by that. So it's just a time, area, humidity difference, or vapor pressure difference, as it's say. So we see numbers like dry cup values and wet cup values, invert cup values. The idea is that dry cup for interior materials, wet cup for exterior, and inverted wet cup for roofing and waterproofing. There's some examples here, some insulation. So insulation is interesting, different types of insulation in our market. We've got foam plastic insulation, so things like extruded polystyrene or XPS, spray foam that's closed cell, polyisocyanurate with different types of facers, expanded polystyrene, or sometimes called EPS. These materials generally at thickness, because of their molecular structure of the foam and the plastic and the bubbles, so essentially the air trapped inside the plastic, you've got tend to be low permeance materials. So foam plastics tend to be low permeance versus things like that are made of wood fiber or open cell spray foam, mineral wool, fiberglass, cellulose. These are more fibrous materials. they tend to be vapor permeable, right? So bad insulation is vapor permeable, but foam plastic insulation is impermeable. And when we start designing roof and wall assemblies, this starts to matter. We also have a whole class of materials now, things that are called smart vapor retarders. And the idea with a smart vapor retarder, it's not so much that it actually digitally does anything, it's just that the properties that, in the case here, nylon, polyamide is the chemical there. So nylon happens to the material itself, the way it's made, the screen essentially changes shape as the humidity is exposed to increases, right? So as the humidity goes up, it actually more molecules will go through it. As the humidity is low, it'll drop down. So this material, the certainty membrane, when it's dry indoors, it's a vapor barrier, but when, say, water got behind the wall, it actually opened up. So the idea with a smart vapor retarder is that if you ever had a leak, in theory, you could dry things through it. The challenge with smart vapor retarders is that you have to put them in the smart location, or have to deal with this properly, because you can't just assume that's going to solve all your problems. It's actually it's dumb in its performance, but it's smart sort of in the properties. Let's say. Wood, so plywood and OSB as a sheathing are also smart vapor retarders, and we call them original smart vapor retarders. And this is an important characteristic to understand with wood, because we tend to use OSB and plywood sheathing all over the place in our wood frame construction. On the inside, when we have plywood on the inside of our building and low humidity levels, 30 to 50%, it's a vapor barrier. It's like, or vapor retarder. It's very low. It's like half to 2 perms. So plywood sheet, let's say on a wall here, outside and inside, a plywood sheet in a deeper wall like this, or a roof truss on the inside, so if we move the sheeting to the inside, it would be a vapor retarder. That exact same plywood on the outside and exposed to outdoor humidity levels, which tend to be 80 to 100%, generally 80% on average year round, and say 90% of the wintertime, plywood is like 20 perms and OSB is about 6. So plywood is more permeable than OSB because of the way it's made, the wood grain, but also the glues that are in OSB. But it's interesting. So you could have plywood on both sides of the wall. On one side, it's a vapor barrier or retarder, and the other side is quite open. And so, things like floors, we have floor sheathing, and you have overhanging, maybe at a window, bay window. You don't need to add a vapor barrier there because you've actually got one through the wood. But then your wall sheathing on the outside is also quite vapor open, so not something you have to worry about. So it's something that, pay attention to what's happening to the material. So material properties generally are, if the plastics you get are like 1 perm is 1 perm, doesn't change too much. But things like plywood and some materials, they actually change. So the placement of the vapor control matters. Okay, so if we put, I talked about earlier on, the vapor retarder, we generally put on the inside or the high vapor pressure side when we tend to get most of our drive in wintertime. And so we put on the inside. If we say made a mistake and put a vapor barrier on the outside, essentially a vapor barrier on the outside is going to do nothing to control the vapor that's going through that assembly. And it's only going to act to prevent any drying out, right? Because you put it in there, the water vapor still wants to keep going through it. And the water vapor molecules are hitting that, and they're, you're accumulating moisture within that sheathing. So these are actually examples of real walls that were accidentally built with vapor barriers on the outside. And you can see the mold growth in the case here and the corrosion and damage to steel. You can actually see the liquid water here. So these were walls with insulation and then a vapor barrier on the outside. And these are vapor diffusion problems. Claddings. So, a lot of metal claddings, products like fiber cement and other panels that are made of, high density materials. Materials like these materials themselves, if they're installed tight and they're impermeable, they also can function as a vapor barrier on the wrong side or on the exterior side. And so, the way we typically address impermeable materials is we allow a bit of airflow behind. So if we have a vented or ventilated airspace, we can address that. So, the notion of a rain screen or just providing a gap or things like vinyl siding, which have a lot of holes and gaps and things like that, they work because there was a gap behind them and they didn't trap that moisture. Although if you took a giant sheet of cement board and slapped it on the outside of a wall and didn't address vapor on the inside, you would actually run into a vapor diffusion problem. In roofs, so where we run into a lot of impermeable finished materials is in the roofing industry, right? So asphalt shingles, EPDM, PVC, SPS, torch-on roofing, these are all impermeable materials, and they're on the outside of our building enclosure assemblies. And so the way we address impermeable materials on the outside is that's why we ventilate below. If we didn't have airflow from the outside ventilating in this assembly, we would end up with moisture accumulation in the sheathing below that roofing membrane because of vapor diffusion. Okay, so vapor diffusion is that, or sorry, airflow in the case here is essentially negating or taking away the moisture that's coming through by vapor diffusion, right? So that, so many grams per day are coming through by diffusion, and the airflow of the ventilation there is taking that away with an air exchange. Okay. When we look into building enclosure design, one of the things that we want to watch out for or careful with is something called a double vapor barrier, especially if between those vapor barriers we have wood or steel or some sort of moisture sensitive material. And so the notion of a double vapor barrier is you've got low vapor barriers, so say poly on the inside, and then you have a low vapor barrier material on the outside, so say metal cladding that was right tight to it, or an impermeable peel and stick, or a thick foam plastic or a foil-faced insulation. So if we had two vapor barriers, and if we have double vapor barriers and moisture can get into that wall, either it's built in, so you have wet wood to begin with, you have a rainwater leak, or you have air leakage, then what can happen is moisture can get in, but the only way that moisture can get out of these enclosed assemblies is by diffusion. And if you have a diffusion barrier on both sides, it can't get out. And so the concern with a double vapor barrier is moisture getting in, there's just no way to get out. You get in, can't get out. You get in, can't get out, right? So there's a bit of a fear of a double vapor barrier that we tend to try to avoid. There are some assemblies where this can work and can be managed, but generally not when we have materials that are moisture sensitive mold or could grow mold, right? And so this is how, part of the building science design is avoiding this or preventing the conditions for condensation from occurring inside that assembly. A good example of an intentional double vapor barrier assembly is a conventional roof, where we've got whatever roof is, metal deck or wood, we've got an impermeable vapor barrier, temporary roof during construction, and then we have foam plastic insulation, and then we have a exposed roof membrane. So we've got impermeable, a whole bunch of impermeable insulation, and then impermeable membrane here. This works just fine until, and when we have roof leaks, the water gets in here and wets the insulation. And as long as the moisture can't get through the green layer here, then it'll just sit there forever and slow, you lose some of the R value of the insulation when it's wet, of course. But it's not not necessarily damaging the rest of the structure here. The risk, is if we had wood or something in here, or let's just say this membrane wasn't, done really well, made holes in it or something like that, we could eventually get moisture that's, going to drip down into our building. So we do have these scenarios in building enclosure design where we have double vapor barriers, but generally we try to avoid this. So controlling diffusion. So we typically, when we look at vapor diffusion to start, it's often a vapor retarder question. Do we need a vapor retarder? How do we, what is it? Where do we put it? When we add insulation to assemblies, that's another way that we can control vapor. Okay, so in a wall assembly, let's just imagine a 2x6 wall here with wood sheathing. We got a vapor control layer on the inside, and we have now added a bit of exterior insulation. So what exterior insulation does, so we got hot inside, cold outside, we got a rain screen cladding with some whatever type of insulation here. When we look at adding the insulation, so instead of the location here being really cold, it's warm, right? We got a bit of insulation on the outside relative to here, therefore the sheathing is warmer than it would have been before. And as we increase the temperature of that sheathing, as we add more and more insulation, so we've gone from cold to not so cold to pretty much indoor conditions, the risk for condensation within the assembly drops, and it drops pretty significantly. So if we're trying to prevent condensation from occurring here, if we add more insulation, the warmer this is, the drier it's going to be. And so what you'll actually see, so in this scenario here, we might need a vapor control layer on the inside to prevent the molecules from getting through and condensing. In this scenario here, we can say, okay, you know what? I've got enough insulation here. Maybe I just need a vapor retarder paint. And maybe here, I've got so much insulation on the outside, I don't need a vapor barrier anymore in this wall. The vapor is being controlled by the insulation, and the sheathing itself is now being a bit of the vapor control layer. And so we get all these questions all the time. Well, how much insulation do I need to add so I don't need to control vapor on the inside? And the answer is, as much as you can. There are some tables, and there's some tables you can put together if you're curious about this. Or just some good rules of thumb that come up, and what it depends on is what the indoor condition is, the indoor temperature and the humidity. And the reason this matters is how much water vapor molecules there are indoors relative to outdoor conditions. And so you got indoor temperature and humidity, and then you've got outdoor temperature here. So the indoor temperature in this case is assumed to be 21 degrees. And then we got outdoor temperature. So if we assume it's minus 20 degrees on average, and the humidity is say 40% inside, it's quite maybe humidified. This tells me that I need 65% of the insulation on the outside. Okay, it's just it's a good rule of thumb to start the discussion. And you'll actually notice here there's like this 2/3 sort of 65% line here. And generally in the industry, to be conservative, for years we said just put 2/3 of the insulation on the outside to be safe. And that generally works. It doesn't work if you have high humidity in indoor spaces, and it's probably too conservative if you have really dry indoor conditions, right? So if it's minus 20 and it's 20% indoors, you really could get away with like 41% without any need for vapor control on the inside. And so this is sort of a first conservative sort of single point dew point assessment that you can use to say, okay, how much insulation do I need to put in here? And that's one of the things that designers will look at. The other thing to factor in is what type of insulation you have, and that comes in as a secondary discussion to this. If you have exterior insulation that say mineral wool, wood fiber, fiberglass, cellulose, that is a high vapor permeance, what happens is your water vapor will just go through it, right? So if you have permeable insulation on the outside, vapor diffusion just keeps going through, and it doesn't, it isn't slowed down by that insulation. High vapor permeance insulation, you get drying should that sheathing get wet in both directions. The vapor control strategy, as you add more insulation, the need to control vapor on the inside drops. And so the thicker the amount of insulation you get to that 2/3 or so, depending on your building, then you don't actually need a vapor control layer on the inside. You've got enough insulation to keep everything warm enough. And then with smaller amounts of insulation, then you need to look at, okay, well, I could put something in here. What does it need to be? If you use low permeance insulation, you can use both. And the reality is you can use both. You just have to treat the design slightly differently. So high permeance works to flow through. Low permeance exterior insulation, so foam plastic insulation, we just have to appreciate that we're not going to get a lot of flow through it by diffusion. And therefore we have to rely, if we want to avoid that double vapor barrier scenario, then we have to allow drying back inwards. And if we allow drying back inwards, that means, smart vapor retarders and things like that certainly can be helpful. But what it means is that we want to not put a vapor barrier on the inside, so we can allow some moisture, if it does get in there, to go back through it, through the inside. And so if we take away the vapor control layer in the inside, we need to have a high enough ratio of insulation on the outside relative to the cavity so that we don't get condensation occurring in there, and we have enough that we can dry that out. Okay? And so when we talk about exterior insulation, is about the ratio, and with the ratio, we then look at the vapor control provided by the insulation, but also by the inside. So some case studies. So the problem with vapor diffusion that we run into in the industry is that improper control will result in elevated humidity levels, condensation, and wetting within spaces that we can't see, so concealed spaces. And it creates that risk of fungal growth and deterioration that slowly occurs over time that we don't know about. When we look on the flip side, not thinking about drying or not considering the drying out ability of assemblies, when or where moisture becomes trapped, right? So due to built-in construction moisture, so if we're building in a wet environment, we just slap everything together, it's not going to be able to dry out, we can run into problems. Or where we may have leaks in service. And there's been, numerous, building failures, clusters, leaky condos, things like that, in BC and elsewhere, where water got in, window leaks and window corners. And so, if we want to have some resiliency against small leaks that are likely to occur, then we really need to think about, all right, how can I let that assembly dry out? And that's generally why, things like house wrap, liquid water can't get through, but then also vapor can get back out should things be wet underneath. So recall, vapor diffusion is small, right? Small amounts, but important amounts. Also realizing that vapor diffusion can also only dry out so much too. So if something does get wet, vapor diffusion may not completely save you if you get too much water in there, right? So trying to dry out a third of a liter of water if you've got rainwater pumping in there every time it rains is not going to help. So we have to address that as well. So the difference between water leakage, air leakage, and vapor diffusion. These are photos here showing water leakage problems. These are, classic, British Columbia leaky condos. We're also seeing all over the place, Alberta, even in the Yukon and Ontario and other places where water has gotten in at details, below a window that didn't have subsill flashing, at a balcony saddle here, a wing wall. Water gets in over 5 to 10 years or longer and rots away the structure, and so much that you can kick right through it or pull it away by hand. Air leakage condensation can also cause moisture problems and damage. Examples here, this house in Minnesota, actually is a whole subdivision like this where slightly pressurized, cold climate, so air leakage through really bad air barrier details or lack of air barrier details, electrical and then wing wall or partition walls running in, resulted in persistent air leakage condensation, and then over a number of winters, mold growth and then decay of the OSB in the case here. So this is an air leakage, and air leakage problems tend to be concentrated around some sort of defect. Vapor diffusion problems tend to be smaller, especially, but more widespread, right? And so when you have a vapor diffusion problem, it's not going to occur just in one bay, it'll occur sort of everywhere if that diffusion hasn't been addressed universally, right? Because it's sort of a one-dimensional phenomenon, not three-dimensional like a rainwater leak or an air leak, tends to universally cover the whole thing. That picture I showed earlier on the right, this is the assembly here. So they steel stud wall, bad insulation, blue skin, which is an impermeable peel and stick membrane put on the outside. They put some insulation on the outside, the design team here, but they didn't put enough. And what happened is they didn't have any vapor control on the inside. The humidity was elevated given the use of this space. It was indoor, it was a residential building, multifamily, poor ventilation. So the humidity in the wintertime tended to be 50, 60% in Vancouver. But they didn't have enough, vapor control or, no way of drying on the outside. This could have been solved. If they had doubled the amount of insulation here, this would have been fine. The problem was this building was built to the minimum under the building code. So in the building code 925 actually allows you to have insulation ratio tables there. And the insulation ratio tables are right on the line. If you just meet those, you'll be lucky. You need to make for sure that you don't have elevated indoor humidity conditions with that scenario. So in the case here, it met the code, but it had too high of indoor humidity, and therefore it failed. And so that's why the insulation ratio I talked about earlier on, really careful, need to pay attention to. And this, if this had been a permeable membrane here, this actually would have been fine. It's just the fact that it got trapped in there. We've seen numerous examples of this scenario here. This is a unique one, a white colored roof membrane in Ontario. It's an unvented roof, spray foam roof. And the interesting part of this one is it had a vapor barrier, but it was ineffective. It was essentially bypassed. And I'll explain what that means in a second here. So if we look here, they're cutting open the roof. And if you ever cut in the roof and you find the shielding like that, you kind of want to turn around and get off the roof. But the roofer here can cut in here, and he cut into the OSB sheathing with the X-Acto knife. And you can see here, so the assembly was white membrane, protection board, gypsum protection board, OSB, and then in here we had open cell spray foam. So open cell spray foam is vapor open. It's not a vapor barrier, but it's relatively airtight. And the assembly here, so we have all, you can see here, the OSB, it's all totally destroyed. Is we have a foot of open cell spray foam below, ½ inch, or now it's like swollen up to like 3/4 of an inch of OSB. The assembly here essentially looks like this. It's not the same one, but it looks like this from the inside. You got the open cell spray foam, and they had, they actually put, because open cell spray foam is not a vapor barrier. If this had been enclosed cell spray foam, it would have slowed down the vapor flow. Because it was open cell, they added a vapor barrier. They added polyethylene here. Now, what's interesting is they put polyethylene in the ceiling, but there was quite a few gaps, sort of like this, between the polyethylene and the insulation, so much that the air, and there were pot lights and bathroom fans and all sorts of things running below here, so much that the vapor barrier they put in there was bypassed by air exchange. There's just so much. And essentially the air in that space there was the same as indoors by all the holes in this layer here. And we ended up with vapor diffusion through the foam condensing and persistently condensing for a couple of years. And because it was a white colored roof membrane, it never got the solar energy to dry it back out and got destroyed. So with especially white colored roof membranes and open cell foam, there's no venting in here, you notice. So unvented roof, you need to be really careful with vapor control. You actually get effective vapor control. You're not bypassing it by air leakage. A lot of spray foam manufacturers will say you can paint the spray foam. The challenge with painting the spray foam is getting an effective vapor barrier out of that. And that's being proven to be a challenge as well. So you got to be really careful in this scenario here. You really want to fill in all those voids. You overspray the spray foam, scarf it off, and then make sure that you're not penetrating with too many holes. So when you look at spray foam, you have the open cell spray foam, just like I showed there, which is vapor open. Closed cell spray foam, or 2-pound spray foam, like people call it. The closed cell spray foam is higher density, and it is actually, by the virtue of the way the cells, so they're actually closed off rather open instead of the open cell. And so we use a closed cell spray foam is, we look at the assembly here. This is fill the cavity with closed cell spray foam, and it'll be a problem, or won't be a problem. And so in a closed cell spray foam roof, vapor flow is managed by the spray foam as the vapor barrier. Okay. The problem with closed cell foam is it's quite expensive. It's quite a bit more expensive than bad insulation. And so there's a desire to reduce the amount of spray foam that you might use. And so what you can do, and this is all over US building codes, not so much in Canada, but what you can do is you can reduce the amount of closed cell spray foam. You put the closed cell spray foam on the sheathing, and then you fill the rest of the cavity with cheaper baths, right? So closed cell spray foam is like $1 a board foot, and which is an inch. So every square foot by inch is about $1. And bad insulation is like a tenth of that, right? And so using cheaper insulation, but it's vapor open, closed cell there. And so the idea is if you have enough closed cell foam, you can put the bad on the inside. So there are these ratios that you can play with in the code to do that. The challenge is if you don't put enough closed cell foam, and you can see this is the attic here, you can see what happened. So they didn't have enough foam in this roof, and the humidity would just go through and it would condense on here. So this is a good example of a vapor diffusion problem. You can see the insulation all falling out of this attic. And the problem that occurred is they didn't have enough insulation for the humidity that they ran into. Now, in cold climates, especially the north, we need to be really careful with high humidity spaces like pools, right? So pool buildings, you know, any place where the humidity is actually, you know, pumping in humidity. You know, pools, aquatic centers, museums, and especially places you might pressurize as well. That's where an air leakage problem, but also addresses sort of comes into play here. And so in the case here, we got an unvented roof, shingle roof, we've got closed cell spray foam, full depth, right? And so this is a vapor retarder. We got a vapor, you know, impermeable roof membrane here. But in a really cold climate where we have persistent vapor flow pretty much year round outwards, you can still get accumulation. So this is an example here in a really cold climate where they had asphalt shingles, roof underlayment, OSB sheathing, closed cell spray foam. There's some issues with air leakage that built up joists, but universally across the entire assembly ran into vapor diffusion problems just because over time the vapor was just going through. And so the case here is that vapor, the impermeable spray foam actually wasn't impermeable enough for the loads. And so what we find in high humidity occupancies in anywhere north of, you know, 50 something degrees, you know, in Canada, or it's actually climate zones 5 and colder, we really need to be really careful. And so in those cases there, we tend to avoid putting insulation into wood frame trusses and cavities like vented roofs. And we try to exterior insulate as much as possible. So in cold climates, you can look at the vapor diffusion. You need to look at it carefully. It will fail these buildings. But we find that exterior insulation, so putting all the insulation above your structure, keeping everything nice and warm, and no risk of diffusion, condensation in the indoors, then that's your way to go. So air tightness, but also vapor diffusion control. Basement walls, above grade and below grade basement walls, you know, cold concrete, impermeable, so there's no real flow through it by diffusion. It's always a challenge, right? You put bad insulation in here, any, you know, defects from air control or vapor control, you get condensation all over the place. Excuse me. You know, one of the ways that we design wall assemblies is we'll put a foam plastic insulation against the cold concrete so that instead of getting condensation on the concrete, we've warmed up that condensing plane by that insulation. So again, it's an insulation ratio question. How much is coming in versus, you know, the temperature at our sheathing plane here. So the typical strategy is put foam against the concrete, take the foam, make it airtight. It's vapor tight by its properties, and put insulation in the inside. In the scenario here, not having enough exterior, not having enough foam insulation relative to the bad insulation, and you end up with condensation all over the inside of the assembly. So it's important to get the ratios right. It's important to get enough, and when in doubt, more foam, less batt, or no batt, even better. Many scenarios of vapor barriers in the outside of wet wood. We've got to be really careful with peel and stick where initially wet wood may be used or water got in during construction. Base of wall, you know, below grade to above grade transitions where you have impermeable membranes. If water is able to get in or is in initially, this is what can happen at the base of your entire building. It's all rotten because of lack of drying there. So you need to be really careful. We tend to use impermeable materials below grade because they're good for waterproofing, but where we use them, we need to watch the extents and also make sure we're not trapping moisture in. Neat little case study here. This is a building in BC, in a very wet part of BC that was built wet. So all the wood was soaking wet during construction. They wrapped it in building paper, and then they wrapped in a standard practice for some time in the 90s. Even now, we still see a bit of it, was to wrap building paper corners in blueskin or peel and stick. And peel and stick is impermeable. And so they were wrapping impermeable peel and stick for 4 or 5 inches. You know, they take an 8 or 9 inch roll of peel and stick and wrap all the corners. And this entire complex, almost every single corner was rotten. And what happened is the water was initially wet. They wrapped it in impermeable peel and stick in an outside corner. Not a lot of heat flow through there. Even though it's a rain screen, even though this is an interesting one for builders, even though the peel and stick was over top of the building paper. There was a thought for a while that you know, if you had peel stick on top of the building paper, the moisture would somehow diffuse underneath and dry out. It's not really proven out, and hasn't really worked out that way in a lot of cases. So impermeable, no over drying, and essentially, you know, just sat wet for years and resulted in pretty good damage there. Case from Whitehorse there as well, a north side of a wall assembly that got wet. And interestingly, you know, you got a vapor barrier on the inside, you've got OSB sheathing, you got vinyl on the outside here on house wrap, and just really not enough drying ability to dry that moisture that was able to get in back out, right? So the wall here had, you know, foam as a vapor barrier on the inside and poly, but, you know, given the climate, especially north side and Whitehorse there, not enough solar energy to ever dry this out. A rain screen certainly would have helped, but also addressing the moisture source to begin with there. You know, we run into new things all the time, but, you know, what we're seeing, you know, in terms of building materials now is constantly changing. You know, and it's something to look at from a risk standpoint. Wood fiber insulation is, people are looking more and more at it for sheathing material. So this is a wood fiber wood fiber sheathing with a high permeance. But again, high permeance got wet during construction, north side of a building, there's just not enough energy to dry those things out. So assuming because it's permeable, that it'll dry itself out is something you need to be really careful as well and have to address. So in the assembly, here is a passive house building, a lot of insulation, very little outward drying, wet sheathing to begin with, facing north, and just sat there for long enough to deteriorate, cause a problem, and have to be rebuilt, or part of that building had to be rebuilt. So diffusion matters, but it also, you know, there are scenarios where we just won't get diffusion. There's certain assemblies, like where if you put all the insulation in that cavity, they're just not going to dry out. Double vapor barrier examples, you know, a high-rise building here, actually, high-rise building, brick cladding. You see the peel and stick on the outside, and you're, well, where are the insulations behind? This can't be good. The poly on the inside. And this was a huge high-rise building where they had dryer exhaust. I'm sort of out of the picture here, but dryer exhaust that was leaking into this cavity. So warm, humid air leaking into this cold cavity, condensing and getting trapped. Floor assembly, vinyl, carpet tile, roof membrane from the modular building below. Water just sitting in there for 2 years, and this is the type of damage. So again, not only exterior assemblies, but also interior assemblies. And really the only way to dry this out is by diffusion or pumping air around in there. So really careful about, you know, trapping wet materials into building construction for things like this, of course. Now, we talked a lot about Canadian problems, you know, cold climate problems, inward vapor drive. So vapor drive typically is, you know, it's always high to low pressure. But in the summertime, that can reverse, right? And the problems we can run into in Canada is if we have, say, a cladding like, you know, a brick cladding or a stucco cladding, and that's directly applied over, say, sheathing. What will happen is the rain, you know, say rainwater wetted cladding, sun comes out and the vapor drive actually reverses, and then we get condensation on the inside of our vapor barriers, right? So this can happen if we have really absorptive claddings. One way to address this is with a rain screen. So we ventilate and drain that space so the airflow there can decouple that. Or we can use things like smart vapor retarders that in the case here, when the condensation hits that smart vapor retarder, it actually keep going through. Okay. And a real hot, humid climate problem is a lot of buildings, like a lot of hotels in particular, where they use vinyl wallpaper on the inside. There's, you know, persistently that vapor drive from outside to inside. Places like Hawaii and Florida, where we all can't go nowadays, but someday soon. If you look at a lot of those hotels, you pull back the vinyl wallpaper, there's tons of mold behind there because they've been getting persistent in the vapor drive. So a little quiz to make sure we've all been paying attention. You know, what's wrong with the photo in this, or the photo in this cold climate example? Right, I got brick cladding going up, and I got something impermeable air, vapor barrier, water resistant barrier membrane. And the first question you should have is, where is the insulation? The insulation is not going to fit in this little cavity. It's got to be in the inside. So if this is a cold climate and you see, impermeable membrane on the outside, whether it's blue skin or whatever it is, really need to think that, well, someone's really made a mistake here and built this improperly. And this happened. This happened numerous times I've seen, where someone will put an impermeable membrane on the outside because the spec was written so poorly, or the drawing note said the wrong thing. So we don't put vapor barriers on the outside. There are permeable versions of this now that would have solved this problem, but a big problem, and the only way to address this with brick is to rip it all down and redo it. Now, that doesn't, this is obviously a bad problem here. We have a lot less peel and stick in the case here, but this is still a problem. If we have wet wood, all these areas where we have this flashing membrane will actually potentially trap moisture. And so when we look at flashing membranes and details like this, we don't need 12-inch rolls, especially don't need it at all these locations that they've shown it here. So when you get into the detailing side of things, we need to be really careful with what we do. So how do we analyze and how do we design for vapor diffusion? There are simple tools. I shared that spreadsheet to look at insulation ratios. You can do a spreadsheet analysis to look through this. There are tools, things like Woofy, a program called Woofy, if you just Google it. You can do computer simulated hygrothermal analysis, which looks at an hourly simulation of your assembly. And in those tools, you can build a wall, and then you can say, what is the impact of putting a vapor barrier on the inside of that wall or not? I can put it in Whitehorse, I can put it in Hawaii, I can put it in wherever I'm designing, and I can understand the impacts of vapor control there. Becoming more and more common wall assembly for deep walls, like, okay, I got a wall here, double stud wall. Should I put poly in here? Can I use OSB? Can I use foam? So you can help analyze these walls to see what would work best for your project. And you can also understand the implications of different types of exterior insulation and when you may need or not need an interior vapor controller. So lots of tools at your disposal. All the case studies there. If you were to run these through a program like this, you would see a potential problem. So it's something that as engineers you can use as a design, in the building science design aspect of this. So in summary, vapor control, while small, is very important for dry and durable enclosures. Even though it's slow, it's persistent, and it's something that is just there by that vapor pressure difference. It can cause sufficient wetting in many examples, and usually the problems you run into are buildings that are high humidity environments, things like pools, and accidentally wetted materials like construction. We need to design to control the wetting, so that's why we have vapor retarders and vapor barriers, but we also need to design to allow drying, right? And so this is where we watch double vapor barriers. We need to watch the one, look at one-way drying and look at the material selection very carefully. We have tools, and you can use those tools to assess risk and assess your strategies. So with that, thank you very much. And I think we have time for questions, end of the day. Grab that beer and I can hang around and we can chat building science if you want.
Yeah, thanks a bunch, Graham, for your time in developing this. And I just also wanted to acknowledge the support of Engineers Yukon and as well Yukon Housing Corporation. I think I see Jurgen in the participants there and when we developed this presentation the first time that it was run. So I'm just going to launch a little poll with some feedback, and then I think I've allowed everyone to unmute themselves too if they want to just unmute and ask a question directly. Get a little bit of direct feedback going. Maybe a question from me was you talked a little bit about the difference between vapor open and vapor closed insulation materials when you're doing exterior insulation on assemblies. What are you starting to see in the contracting community for what people like using for the vapor open materials? Is there kind of any consensus there, or what are you kind of seeing on projects?
Still a bit of the Wild West. You'll see everything. They're kind of two camps. So traditionally exterior insulation has been for decades, since the 70s, looked at as rigid foam plastic insulation, just because that's were the most common products that were available. Lightweight, relatively, decent costs, XPS and EPS, in that market, and polyiso even to some respect. And so generally that's what was done for decades. And it worked sometimes, it doesn't work in other times, just depending on, what you did for air and vapor control. And the more insulation you use, generally the safer you were, right? Nowadays we have, in the last decade, we've had products like rigid mineral wool, more commonly being used, rigid and semi-rigid mineral wool. The fiberglass was there before. Wood fiber insulations making a comeback into that area as well. And those as vapor permeable materials, when you look at sort of the two choices, the impermeable versus permeable, both really can be used. It's just what you use will dictate what you should do then for vapor control and air control and then water control within the rest of your assembly. So both can be used safely. It's just you have to think slightly differently. You can't just substitute like EPS for mineral wool, for example, without rethinking vapor control and even water control for that matter. So in markets like Ontario and Quebec, we see a lot of foam plastic, and it works. You get enough insulation there, and it tends to be. We're not as concerned about rainwater necessarily getting into that assembly. You get enough insulation to control air leakage, then it can work quite well. In British Columbia, where because of passive house requirements in our building code and step code, we're seeing more and more amounts of exterior insulation. And in BC, there's a paranoia of water, rightfully so, because of leaky condos and other problems. And so builders here have taken a more cautious approach, and they have been concerned about trapping water. So a lot of them have chosen to use mineral wool, as an exterior insulation, and that's vapor permeable. So if water got behind it, it could dry out. Or if they're using foam insulation, they're paying a lot more attention to the detailing, so water can't get behind it, right? When we look in the north, EPS, because of its cost, you're using thicker amounts of insulation anyways. EPS tends to be quite common because it's relatively cheap, and it works. It's relatively impermeable, but thicker amounts, but thinner amounts, it's like a couple perms, so it's not completely closed off, say like a foil face membrane. So we do see this sort of everything being used, and if carbon is your goal, or environmentally and sustainability, then you're going to be looking at the embodied energy and the materials. So we're seeing more and more of that. We're seeing people look at using wood fiber insulation now because they want something with lower carbon than, say, a foam plastic. We're seeing a lot of mineral wool used because of fire. It's just safer to use than a foam. But foam is lighter, and it's can be cheaper in many markets as well. So there's just constant holding in different directions. So the key thing is to, whatever you use, there's sort of different guidance you'd follow to make it work right.
It's just know what you're getting into and what you're using, and using the right spot. And yeah, what you said about embodied energy really resonates with me too. We had another question come up in the chat from Susanna about how much can building inspectors generally detect about insulation or condensation problems?
Well, it depends where you are, but yeah, so in the past, the building inspector would do a vapor barrier inspection. And then what they were looking at is the plastic, the poly on the inside. Many wall assemblies and roof assemblies no longer use alternates to poly, or you just don't even need. And when going from a traditional approach, the way that everyone built, to dozens of different ways you can build more highly insulated assemblies, I find a lot of building inspectors now they don't know what to do with this. They don't know what to do with it, or they will say, go hire an engineer, or, so there's a lot of work going on to educate building inspectors all across Canada on like, hey, these are new assemblies. The inspection you're doing, that plastic doesn't have to be there anymore, or it doesn't have to be sealed because I got an air barrier somewhere else. So they're already looking at so many different things that now the building science has become trickier. And so there's constant sort of friction now between, builders and building inspectors, because what they're trying to do is better. It's more efficient, it's more durable, but the building inspector may not fully appreciate or understand it because they're not necessarily building scientists. So it's become more complicated, unfortunately. The same time, there's been a lot of guidance put together that, if someone took the time to read it and take some courses or training, then that they, would understand what people are doing. So a lot of builders are now educating building inspectors on what they're doing.
Great. Any other questions from folks? Another one in the chat there about how does Tyvek or similar material, WRB, manage moisture in a wall?
Yeah, good question. So when you look at house wraps, so house wraps like Tyvek, they're vapor permeable. So they're like 10, 20, 30 perms. So they're quite permeable, but they're water repellent, right? So house wrap on the outside of your wood sheathing prevents liquid water from getting the sheathing wet, and then it just drains down, right? So it keeps liquid water out, but it allows that diffusion that's coming through that wall to get out, right? So it's breathable in the fact that diffusion coming from the inside just keeps going through it, like it's not even there, right? But it keeps liquid water from getting in. So it's like a rain jacket for your house, but it's not a traditional rain jacket of a plastic yellow jacket. It's the Gore-Tex, the higher end jacket for your house, right? And now the thing with house wraps, the complication now is like there's like dozens of different types, and they all have different permeances. You can get self-adhered ones, you can get liquid applied ones, you can get impermeable or permeable ones. And so you have to look at the properties of that. And if you're building something traditional and you want something like Tyvek, you need to make sure it's permeable, not impermeable.
Great. I haven't seen any other questions coming in the chat. Anything from you, Robin or Jürgen? Yeah, go for it.
Great, thanks, Tyler. Thanks, Graham. Great presentation. I guess we see a lot up here. I'm work up in Northern BC and Yukon for everyone else. A lot of people using plywood as a smart vapor retarder on the floor with not a ton of insulation, maybe in a 12-inch, 14-inch TJI or something. How do you feel about plywood as a vapor retarder in that location? Thanks.
Yeah, I think, for most, especially, on the floor, you're going to have like floor finishes and other stuff on top. So like you're going to get more things on top of that that are going to resist vapor. But, plywood itself on the inside is a good vapor retarder. And especially if that soffit or that floor is open or open to the outside. So if you had plywood and then say you had something that was impermeable in a cold climate, so say like you put metal soffit, but not perforated, but like something right up tight to that, you could in theory get a persistent drive through there that might cause a problem. So you'd want to look at that. And that's why, most of those soffit scenarios are vented or open, right? So they're not completely closed. And then you also look at, okay, you got more than just plywood. You've got some sort of flooring, whatever it is, wood, vinyl, plastic, on the underlayment that's going to stop the vapor flow through there. The riskier scenario there is like potentially air leakage at your rim your joists. And, if that plywood is also your air barrier, you need to tape and seal it. And more importantly, when you look at air barriers, which you need to talk about here, but air barrier continuity, that floor and whatever you use there, chopped up little pieces of plywood, that also needs to be airtight, or something else has to be airtight in there. But from a vapor diffusion standpoint, plywood and OSB work sufficiently well as long as you have, say, venting or ventilation on the outside. So like a rain screen type scenario. and in a normal humidity environment. I would not rely on plywood in a pool building to be a sufficient vapor barrier, because the humidity indoors raises the permeance. I wouldn't use a smart vapor retarder in a pool building either. You need something that actually is going to stop that vapor.
Great. Any other questions from the audience? Otherwise, I guess, yeah, thanks everyone for coming out on your Friday evening here, and thanks to Graham. Hope everyone enjoyed a few beverages and a little bit of demonstration of condensation on an impermeable surface, and enjoy your weekend.
Thanks, everyone.
Thanks.